Imagine a world far stranger than any science fiction story, a world where things do not exist in a definite state until you look at them. This isn't fantasy, it is the bizarre reality described by quantum mechanics. For over a century, physicists have grappled with the rules that govern the universe at its smallest scales. Atoms, electrons, photons that make up everything we see behave in ways that defy all common sense. At the heart of this puzzle lies a profound and unsettling idea known as the Copenhagen interpretation. It suggests that the very act of observation plays a role in creating the reality it seeks to measure. This is a complete departure from the classical world we experience every day. In our everyday lives, we assume objects have properties whether we are looking or not. To understand this strange new reality, we need to grasp its two foundational pillars: wave-particle duality superposition. First, let's consider duality. In our world, things are either particles or waves. A grain of sand is a particle. A ripple on a pond is a wave. They are mutually exclusive. But in the quantum realm, this distinction dissolves. An electron, a photon of light, any other fundamental entity, can behave like a particle in one experiment and like a wave in another. It's not that it is one or the other, it is somehow, incomprehensibly, both at the same time. This dual nature is proven in experiments. The most famous of these is the double-slit experiment. If you fire particles like tiny marbles at a screen with two slits, you expect to see two bands on the detector behind it corresponding to the slits. But when you fire electrons one by one, they form an interference pattern, multiple bands. That pattern implies a wave passing through both slits and interfering with itself. Each electron alone seems to go through both slits as a wave of potential. The quantum world needed new prophets. They arrived in the 1920s, Niels Bohr and Werner Heisenberg. Working together in Copenhagen, they became the primary architects of this new interpretation of reality. Bohr, the philosophical father of the group, insisted that we must abandon our classical pictures of the world. Heisenberg, Bohr's brilliant protege, provided a crucial mathematical foundation for this idea with his famous uncertainty principle. He showed that there is a fundamental limit to how precisely we can know certain pairs of properties of a particle at the same time. For instance, the more accurately you measure an electron's position, the less accurately you can know its momentum, and vice versa. The act of measuring position, say by bouncing a photon of light off the electron, inevitably disturbs its momentum in an unpredictable way. The most dramatic part of the Copenhagen interpretation, the collapse of the wave function. The moment a measurement is made, this entire wave of possibilities instantly and mysteriously collapses into a single, definite state. The electron that was a diffuse wave of probability a moment ago is suddenly here, a concrete particle with a definite location. For all its scientific triumphs, the Copenhagen interpretation leaves us with a profound sense of unease. It divides the world into two realms: the strange probabilistic quantum system, the solid classical observer with their measuring device. But where is the line between them? At what point does a collection of quantum atoms become a classical observer capable of collapsing a wave function? Is a cat an observer, a camera, a rock? The theory offers no clear answer, creating what is known as the measurement problem. The Copenhagen interpretation forces us to confront the role of consciousness and information in the physical world. While most physicists today would argue that the observer doesn't need to be a conscious human, any interaction with a large-scale environment can cause the collapse. It hints at a universe that is not a static stage on which events unfold, but a participatory reality that responds to inquiry. It implies that at the deepest level, properties like position, spin, momentum are not inherent attributes of particles, but are instead properties of the interaction between the system and the observer. The moon is not there when no one looks, or does our looking bring reality into being?